Okay, so now we're going to move on to our next type of thread. So again, these are all sort of threads with plastic parts, and we see very low strength properties from all of these parts. So now we're going to shift over to sort of getting metal components in. Metal threads, you're using a nut or a heat set insert, will last a lot longer than printed or tapped threads just because the threads themselves are metal. So they're going to have higher material properties than the plastic threads. So the first thing we're going to do is just put a nut on the end of the bolt here. So the nut will be on the opposite face of the bolt. The torque strength here is sort of not applicable because the nut is sort of compressing, or I guess I'll show you once we're over here. But let's go to this demo. Oops. Sorry, this is a little finicky. Can't get my hands in there. There we go. Oh, that's why. Okay. Sorry, this is taking a bit, everyone. Just got to fiddle with the washers here. I have some washers that are sort of distributing the load of the bolts holding everything together, and it's kind of hard to like slot in the. It makes it a little bit hard to slot in these sort of fixture pieces I have. So here we have just a bolt on one side. We have a nut with a washer on it on the back side. This gives us a little less sort of profile advantage because we have, if you're designing this for one of your applications, you'd have to have the bolt pass all the way through the part to the other side and also have clearance for a nut on the other side of your part. But when we pull this, we actually get a whole lot of deformation. What's happening here is the nut, oh, and also one thing to note, all of these parts, I tried to make the bolt side as rigid as possible. So this is a carbon fiber reinforced panel here on the bolt side, which is why it hasn't been deforming as much. But over here, you can see this is deforming a lot. In order to actually fully break this connection, either the part breaks or we have to pull this nut all the way through the part, which means that it's going to be a lot stronger than our other methods where we just had to rip the threads apart. So you can see this is really deforming. This is sort of a beam bending sandwich panel problem, right? So we have, this has effectively turned into a 3-point bend test where we're testing the flexural strength of this beam. So as we load it, it's just going to be bending and bending until it eventually deforms. And you see it sort of broken entirely apart at all of the connection points. It is sheared because the weakest points are the points with the least material, which happen to be surrounding the entire thing. So that was a pretty fun failure mode. This lends itself to like very strong connections. And what we can do here is, as I said, this turns into a beam bending problem because we're pulling on this part and holding it back with these 2 points. So this is where fiber reinforcement can really come into play. I'm going to share my screen and show how we can reinforce this part to be a whole lot stronger. So let's go back into Eiger. And I'm not going to save those changes, but I'm going to go back to one of these parts. And hold on, I'm setting something up over here as well. So I'm going to go back to this part here, and I'm going to reinforce this with carbon fiber. And I've done another webinar on this where I sort of talk about the basics of beam bending theory and how you can selectively reinforce your parts to take advantage of that by figuring out where they're going to be loaded in bending or in tension. So if we go into internal view here, again, we have a bolt sort of, or a nut sort of trying to get pulled through here. And what we can do is we can create a sandwich panel on this layer and on this layer to resist that bending force. So this is about layer 47. So I'm going to use fiber here and create that group. It was either 46 or 47. And so now what we've done is created this sandwich panel. So if any of you are familiar with like beam bending theory, putting your stiff material on the extremes of your beam on the top and bottom surfaces, is what's going to help you out the most, which is why like I-beams have that sort of construction where the thick material's on the top and bottom. What we can also do here is we can put concentric rings of fiber in the in-between area. And this is actually a really neat trick because what we're doing is we're creating a, let me just turn on the fiber view here. So our concentric fiber basically creates this tube of fiber around the hole that we're reinforcing. So not only do we have to, in order to break this, not only do we have to resist these sandwich panels that we've set up here and here, but we also have to pull it through this tube of carbon fiber. So there's a lot of ways in which the fiber is basically scaffolding this beam and supporting this beam. So when we go back to test it, so now this is with two fiber reinforced beams, one on each side. And let me just slot this in here. And there we go. So now when we try to load it, this is a whole lot more force that I have to apply in order to break it. I have a big cheater bar over here so that I can apply more torque. So maybe this will help. And so this beam is just holding a whole lot better. And it's still, I'm applying a whole lot of force here and it's still not breaking. So none of you will need safety glasses when you're watching via the webinar, so that's good. But it's deforming a whole bunch. It still has yet to break. Put this over here. There we go. So now that's finally broken, but that's a really, really strong way to reinforce your parts. And in order to do that, we basically had to break the fibers in bending and in tension. And let me go back. And let's see where the fibers are. Yeah, so basically what happened is this part sort of delaminated and the fiber snapped in a bunch of different places across the part. So that's a really, really strong, really secure way of putting threads in your part, just putting a nut on the back and reinforcing with fiber to get that strength. So let's go back to the forward camera here. So when we have a nut, as I said, actually there's sort of two ways. Where's the eraser? Here it is. I'm going to add a little more space here. fiber.
We did get an interesting comment that says, to be honest, this isn't really putting a thread in the printed part.
Yeah, so that's a good point. It's not, we're not putting a thread in the part, we're just throwing a hole all the way through this is just an example to show, like, if you have that connection all the way through your part, you can reinforce it really, really well to make for a really solid connection between your two parts. So with just a nut, the profile, we do have to deal a lot with the profile. I'd give it a 1 for both with fiber and with, my lines are not straight, for both with fiber and with just a plain nut, because your bolt has to go all the way through the part in order to connect it. The pull strength is going to be really strong. The pull strength for plastic is okay. For fiber, it's going to be really strong. Installation, we do have to sort of screw it on there with a hex wrench or a socket or whatever. So it does take some work to install. So I'm going to give installation a 2, and then wear lifetime. Again, we're not even dealing with plastic threads here, so this is fine in terms of wear. So I'm going to give that a 3 because basically it's all up to the part strength at that point, especially if you work with fiber. So the next sort of step up from there, depending upon what you want, because this is not very low profile. So there's a couple ways that we can put threads into our parts to avoid having to, have that clearance for a nut on the other side and have your bolt go all the way through the part. So in terms of the clearance, let's go to the top camera. One way we can get around this is, here we go. This is a secondary version that I've done where, that's not quite in focus. Secondary version I've done where I have a nut embedded or sort of captive in the part. So this is what I call a captive nut. I've designed a little hex cavity inside of the part to accept that nut. And that means I actually have to use less tools. So this is sort of like embedding an insert. I don't have to use like a socket wrench or anything on this nut because the cavity will handle that just fine. But the bolt still does have to go all the way through the part. So that's one way of solving that. The other way is by actually printing a part and adding a pause in it and then putting in an insert. I'm going to walk through the strength of this for now just to show you. It's going to be pretty comparable to what we saw with the bolt all the way on the other side. But there is one major difference, which is that the area that we need to pull the nut through has decreased. So it's sort of like we took a beam. If this piece of paper is my beam, we had a nut on this side and the bolt coming through from this side. And if we make that nut captive so that it's sort of depressed into the part, we're reducing that effective area that we need to pull the nut through to about here. So your beam gets thinner, so the part is going to be a little bit weaker than with a fully all the way across nut. So when we test that, again, it's still pretty strong. And here you can actually see what happened here. This is really cool. That nut was pulled through the plastic. Again, because we have less area to work with because the nut has decreased the effective thickness of the connection. So it's a little bit less strong than just putting a nut all the way on the other side. Can we go over to this other vise here, Marco? One of the things that is pretty, the torque strength on these And just to clarify, those parts did not have carbon fiber in them. That was just a flat basic beam. You can put carbon fiber in them like we did with the other ones, but again, your effective beam thickness is smaller because you have to put fiber below that cavity rather than at the face that you're bending at. Other thing about captive nuts is they probably have a little, when you're applying torque to them, it's basically the faces of the nut butting up against the face of the part. So I'm going to go ahead here. I'm starting at 4, screwing my nut in. So now this is 6. It's still, okay, I'm going to go up to 10. So at 10, what happened here is now I can screw the nut actually turns within the cavity. It's kind of hard to see here. Let me pull it out and sort of show you a close-up with the camera. But what's happened is I was able to pull the nut when I unscrewed the bolt. I pulled the nut out along with it. That's because when I put this nut in and then I started applying enough torque, the nut started spinning within that cavity because the hexagonal shape of it doesn't apply that much resistance to the shape of the cavity. So there is one way to get around that and improve your torque strength, and that's by using a square nut instead of a hex nut. So I have the same part here except with a square nut. And, oops, let me get this part out. And so that setting, the torque setting that I just got to was 10 with that one. With the square nut, what you have, oops, I dropped my bolt. With the square nut, what you have is because of the square faces, you actually have a longer, the square is less of an approximation of a circle, of the hole that the circle's in. And because it's square rather than hexagonal, you sort of have a longer lever arm that can resist torque more easily. So when I screw this in at 10, that holds. So I'm gonna keep increasing, get up to 12. That's 14, 16, and now the square nut is actually spinning in that cavity. So the square nut has a higher torsional resistance than the normal hex nut. So if you're embedding nuts into your parts, I would always suggest square nuts because that torsional resistance is going to be improved. We got about 60% higher torque setting with the square nut than with the hex nut. Going back to the different types of nuts over here. So the profile, similar to just putting a nut on the other side when it's captive. The profile is still a 1. You still have to have your bolt all the way through. And you also have to have enough room around for your hex nut or your square nut. Your pull strength is still pretty high. So I'm going to put a 2, could be a 3 with fiber. Your torque strength depends on whether you're using hex or square nut. So I'd say torque strength is going to be a 3 with hex, or just a 2 with your normal, 3 with square. Or a 2 with hex. And then installation is a little easier than just putting a nut on the back. You don't have to have a second tool to screw the nut in. So I'm going to give installation a 3. And then wear or lifetime. Again, it depends on whether your bolts are more, if there's going to be more torsional loads or pull strength loads. But the wear, I'd also give a 3 because the threads aren't wearing out. But the part is wearing out actually, and that so it could be like 2.5 or 3, something like that. But the threads themselves aren't wearing out, so you don't have to worry about that. It's really if these parts are going to be experiencing a lot of torque, a lot of screwing things in and pulling them out again, then with hex nuts they'll start to slip and they won't be secured or captive inside the part anymore. So I'm actually going to put, like a 2.5 for this one. Okay, so the next category of parts, sorry, my lines are just all over the place today. The next method that you can go about doing this, I'm going to go back to sharing my screen and go to Eiger so I can show you what I did. This is pretty common practice in additive manufacturing because it's a very unique way of going about things where what you can do is you can pause the print and embed a nut inside of the print as you are as you're printing it. So this part, I actually need to turn supports off for this. For a thing like this, I'll show you once it's done pathing. We'll go into internal view. And so what I've done here is I have this cavity, and I put a square nut in that cavity. And then once I get to where that roof of that cavity starts to form, I'm going to hit pause. So the printer will pause. It'll send me an email saying, hey, I'm paused. And then I actually went in and I embedded a square nut inside of the part during that process. And then the print continues over that square nut. A couple people, when I've talked about this before, have asked whether, basically, like whether you can do this, like if you have a part that requires supports elsewhere in the part, can you remove supports from this cavity? What I'd say to that is basically, if you're doing this, supports, and you need supports on, supports will generate in this cavity. But when you're going in to embed the nut, you can just pull those supports out and put the nut in. So it's one of the things about this, the real downside to this method is that you have to wait for your printer to pause to embed your nut in there. And if you wait a long enough time, then what ends up happening is the print will cool, and it'll create this seam at this layer specifically where we're pausing. And that will create basically it's like a crack or a fracture point. If you wait more than half an hour or so, then that really starts to see a decrease in the strength of your part. So while embedding nuts is sort of a neat trick that you can do with 3D printing by putting the nut there in the middle, we see there are a few downsides to this. One is it does really decrease the strength of your part. And two, it is really, like it's a very painful installation procedure because when you're going in and you're embedding that hardware, you have to time kicking off your print such that you are around when that cavity needs to be filled with that nut. And we can see around this time, this is about an hour into the print. So what I did when I did this is I just made sure that when I kicked off this print, I was available in an hour after kicking that off. And then I was able to embed the nut and continue the print. But say you're doing this for a much larger print that could go overnight or could be 12 hours or something like that. You need to be able to know that you can attend to that printer once it's going to pause. And that's the real downside to a method like this. The other thing, and I alluded to this with captive nuts as well, is we're decreasing our effective thickness of our part because now it's only, let's see, this is the actual thickness that is preventing our beam from bending, and that's not that much. So you have to be careful about where you're placing this nut inside your part because when we, here, let's go back to the test platform. Oops. So when we go back to the test platform here, get my paper so that you can see it a little better. And I start pulling out that nut. You can actually see, can we zoom in a little bit more? This is really cool. You can see this, like, the nut is really just starting to pull out of those. You can see that bump there where the nut is pulling out of the plastic. And then There we go. It breaks. It delaminates on the layers. So this, in this way, when you embed the nuts, let's go back to forward view. The pull strength is not going to be as strong as just putting a nut on the other side or even a captive nut, because that effective thickness has decreased. So we're going to make the pull strength is about a 1.5. The profile is, it's going to be better than the other ones, because if you can't have a bolt going all the way through your part, you could put it somewhere in the middle. So you don't need as long a bolt. You don't need to worry about clearance on the other side. So profile, we're going to put 2. Torque strength is going to be equivalent to the captive nut. So use a hex nut where you can, use a square nut where you can. I'm going to put a 3 for that. And then, but installation is just a pain for this one. So that one's going to be a 1, because you have to wait around. And if you mess up, then the part strength is compromised. Can everyone see this okay? Let me move my laptop. And then the wear or the lifetime of the part, I would say this is comparable to captive nuts. So I'm going to put a 2.5. But again, having that pause, if you wait around for a while, causes basically a fracture point in the part. So what that means, and I guess, yeah, it's really hard to see that lifetime. Oh yeah, so you can see that. So what that means is that that fracture point is going to be where your part is going to fail. And so I'm gonna give the lifetime on that a 2. Because that fracture point, that's the weakest link. That's going to be experiencing the most stresses relative to its strength.
We do have some questions coming in around nuts specifically. So Catherine asks, is there a benefit to embedding a nut other than space savings?
Is there a benefit to embedding a nut other than space savings? Off the top of my head, I can't really think of one. The reason why I've seen it to be so common in 3D printing is that it's neat and it's different, right? It's not something you can do in a traditional subtractive process. And so the ability to pause a print and add that hardware in and then have it totally get sealed off is really appealing to some people, because it's just a different way of doing things. But in terms of the strength advantages, there really aren't many. And it's really just in profile. So yeah, that's my take on that.
And then James actually answered that with another idea that the nut is captive, so it can't fall out when it's not in use.
Yeah, that is a great point. The nut's enclosed by the part. If you just had a captive nut on the back of your part and you unscrew your bolt, then the nut falls out unless you glue it in. This way, the nut stays in place. So great point. Thank you for that. Again, some other questions about this. These parts are not reinforced. I've had to put in a lot more strength into torquing them out. But even if all of the parts were reinforced at this stage, when we're talking about nuts and bolts and stuff, I'd expect like the ratios and the different types of strengths that I'd have to apply to be roughly the same, because it's all about like the effective beam thickness. If you put a nut on the back, the beam is thickest. If you put a nut that's captive, then the beam's a little, I'm trying to figure out a better way to explain this. If you put a nut that's captive, then the beam's a little thinner. If you embed it, then the beam's even thinner than that. So if you're putting the same amount of fiber across all of those beams, it's still the thinnest beam that's gonna fail first, and the thickest one that's gonna be the strongest. So it's really just a beam bending problem. But there is one thing that I do want to show you, so I'll share my screen again with you. When we're talking about these captive nuts or these embedded nuts, and we add fiber to them, one way that we can boost the torque strength of the part is by using concentric rings of fiber and putting fiber around the cavity in the part. Because now when you're applying torque to this nut, it's actually, it has to be able to break that hoop strength of the fiber around the part, and that makes it a whole lot, that fiber makes it a whole lot stronger.